Hello friends, we already have become familiar with quantum mechanics by solving quantum particle in a box problem. In this lecture, we learned some classic problems by solving Schrödinger equation for different potentials. We start with harmonic potential. You can think of a harmonic oscillator. In equilibrium, the potential energy is 0. As we stretch or as we compress, the potential energy increases quadratically with x, where x is the displacement with respect to the equilibrium. You can also think of a ball rolling down as shown in this figure. At x equal to 0, it has 0 potential energy. And kinetic energy is equal to the total energy. The potential energy increases quadratically away from x equal to 0. Classically, the maximum height can be climbed depends on the total energy E. So this is the line indicating the total energy. At the highest point, the kinetic energy is 0 and the potential energy is equal to the total energy. The ball cannot travel beyond this point and it turns back. So at this point, it will turn back. This is known as the classical turning point. Now, let us see how do we solve this problem in quantum mechanical way. So first, let us write down the Hamiltonian or total energy operator. So H is given by, so this is the kinetic energy operator, h cross square by 2m d2 dx square, and then we have the potential energy operator, which is given by half m omega square x square. Thus, we write the time independent Schrödinger equation as minus h cross square by 2m d2 psi dx square plus half m omega square x square psi is equals to E psi. Now, let us define non-dimensional position as x tilde. So this is a non-dimensional position. X tilde is equals to square root of m omega by h bar x. So m omega by h bar, if you take a square root of this term has a dimension of 1 over position, and x is, of course, it has a dimension of position such that x tilde is non-dimensional. Now, if we replace this in this time independent Schrödinger equation, then what we get is the following. So minus h cross square by 2m, and then I replace x tilde equal to this such that I get m omega by h bar d2 psi dx tilde square plus half m omega square h bar by m omega x tilde square psi is equals to E times psi, such that minus h cross omega by 2 d2 psi d x tilde square plus h cross omega by 2 x tilde square is equals to E psi. Okay, so this is what is written here, and then we can just write finally this term. Thus, using non-dimensional position, we have converted the time independent Schrödinger equation in this form. Now, for very large value of x tilde, we can approximately write this equation as this. Because if x tilde is very large, then we can ignore this part and we can just write this. Now, approximate asymptotic solution can be written as psi is e power minus x tilde square divided by 2. Let us check this. So, if psi is this, then d psi dx tilde is equals to e power minus x tilde square divided by 2 times minus x tilde is equals to, we can just write it as and if we take the second derivative d2 psi dx tilde square is equals to plus x tilde square and we can write this as x tilde square minus 1 e power. Now what we have assumed, x tilde is very large, correct? So x tilde is very large. So that means again we can ignore this term 1 such that we can write this term as x tilde square x tilde square by 2, which proves that this is a solution for this equation. Okay. Thus, the approximate asymptotic solution is this. Now, let us avoid lengthy derivation and solve using qualitative argument. We know that other than ground state, excited state wave functions must have nodes. This is what we have seen for particle in a box. The ground state wave function does not have any node. The first excited state has one node, the second excited state has two nodes, and so on. But the solution that we have derived so far, right, this does not have any node because this is e power minus x tilde square by 2. So the solution, it looks like this, correct? It does not cross zero line at any point like this. So that means this wave function does not have any node. So this can be a ground state wave function, but this cannot be excited state wave function. Thus, we need to multiply this function with some polynomial, which at this point of time, I just write it as hn of x tilde, right? So this is some polynomial which will be having some nodes. So that means this will be some polynomial which will cross this line 0 at several points, correct? Depending on the energy state. And this polynomial will be having nodes. And if I multiply this part with this polynomial, then the net wave function will also be having same number of nodes as hn of x. So we have to multiply e power minus x tilde square by 2 with some polynomials to get the nodes or zeros of psi of x. So at the moment, we can just write the wave function psi n of x tilde is equals to hn x tilde. So this is the polynomial part, and then e power minus x tilde square divided by 2. So far, we have seen that the eigenfunctions of one-dimensional harmonic oscillators are given in this form. Psi n of x tilde is equals to hn x tilde. So these are some polynomials multiplied by e power minus x tilde square divided by 2. What we do not know is what are these polynomials hn of x tilde. So for ground state, there should not be any node, just h tilde will be equal to 1. For the first excited state, there has to be a node at x tilde equal to 0. So that means this polynomial h of 1 will be equal to 2x tilde, because this has a node, 2x tilde has a node at x equal to 0. For second excited state, we need two nodes, right? And none of them should be at x tilde equal to 0. Note that this is something which is very similar to what we got in case of particle in a box. So now, to meet this requirement that we need two nodes and none of them at x tilde equal to 0, you can just check that this polynomial will meet those requirements, because you will get two nodes in this case at these 2 points. Okay. Similarly, for the third excited state, we need one node at x tilde equal to 0 and two nodes at x tilde not equal to 0. And then you can see, if you look at this polynomial, you have one node at x tilde equal to 0, and you have two more nodes at x tilde is equals to plus minus square root of 12 by 8. So, and then so on, right? We can even derive this for even higher excited states. Okay, and h and tilde x, these are known as Hermite polynomials, and I have shown some wave functions in this plot. So this is the eigenfunction for the ground state, this is for the first excited state, this is for the second excited state, and this is for the third one, and these are the corresponding probability densities. Now we can prove that the corresponding energy eigenvalues are given by this. And note that similar to particle in a box, all the energy eigenvalues are not allowed. And here I just schematically show the allowed energy levels of quantum harmonic oscillator. Let us compare between harmonic potential and particle in a box. Unlike particle in a box, harmonic potential is a finite potential. This remains finite for finite value of x. For finite potentials, a quantum particle can penetrate in regions which are classically forbidden. However, this is not possible for some infinite potential. For example, in case of particle in a box problem, particle remains confined inside the box, whether you treat it classically or quantum mechanically. As you see here, the wave function remains completely confined inside the box. This happens because the potential becomes infinite at the box edges. Since harmonic potential is finite for finite x, we find some small probability of finding the particle beyond the classical turning point shown by these dotted lines. So these dotted lines are the points from where the particle is supposed to turn back in this region. Okay. The particle is not classically, you are not supposed to get the particle in these regions, that is beyond these dashed lines, you are not supposed to get the particle classically. Thus, classically the particle should turn back from these dashed lines and start rolling down the potential in this way. Existence of the particle beyond the dashed lines is classically forbidden. However, a quantum particle can exist there. You can see that you have some probability, although this is very small, but still you have some finite probability of finding the particle beyond the classical turning point. This is related to quantum tunneling, which we are going to discuss towards the end of this lecture. So far, we have discussed about particles confined by some potential, for example, harmonic potential or particle confined within a box. Now we are going to learn about particles which are not confined by some potential but traveling. The time independent Schrodinger equation is d2 psi by dx square is equals to minus k square times psi of x. It looks exactly like the particle in a box problem. However, now potential is zero everywhere. In case of particle in a box, we had infinite potential at the box edges, but now V is equals to zero everywhere. Now, the eigenfunctions are given by psi of x is equals to a e power ikx plus b e power minus ikx. So this is the case of a particle moving from left to right, and this is the case of a particle moving from right to left. And if you put the this eigenfunction in this equation, then we get the eigenvalues as E equal to h cross square k square divided by 2m. Unlike particle in a box problem, there is no boundary condition in this case. Thus, all the energy values are allowed. So, this is what is shown here schematically. In case of a particle in a box problem, all the energy values are not allowed, whereas for free particle, all the energy values are allowed. And now we can write down, once we have the eigenfunctions as well as the eigenvalues, using them we can write down the time dependent wave function like this. And you see the eigenfunctions are now complex, so we can separately plot the real part and the imaginary part as shown here. Now the wave particle duality and de Broglie wavelength, they are given by this. Lambda is equals to h by p. So if we know the momentum, we can define some wavelength, and if we know the wavelength, we can define some momentum and so on. Now, classically, the energy is given by E equal to p square by 2m. And we have seen the energy eigenvalues to be like this, h cross square k square by 2m. So if we equate them, we can define something called a wave number k, which is given by 2 pi by lambda. In 3D, we call it the wave vector, and the magnitude of wave vector is given by 2 pi divided by lambda, where lambda is the wavelength. Thus, classical property of the particle is described by its momentum. Similarly, quantum mechanical, the wave property is described by its wave vector k. Next, we discuss quantum tunneling. We are dealing with a free particle which is propagating from left to the right. It hits a potential barrier at this point. Now, let's assume that the barrier height is more than the energy of the particle. Thus, classically, no transmission is possible and the particle is reflected from this point. However, as mentioned before, quantum particle can penetrate in regions forbidden for classical particles. We shall find the probability that the particle tunnels through the barrier in region 2 and emerges in region 3 to continue its journey. Now, let us write the Schrodinger equation in region 1 and region 3. So, in region 1 and region 3, V is equals to 0. So, that means we can write the Schrodinger equation as this is like in region 1 and region 3. Okay. So that we can write the Schrodinger equation as minus h cross square by 2m T2 psi dx square. The potential energy part is equals to 0, and this is equal to E times psi, such that we can just rewrite this in this form. D2 psi dx square is equals to minus 2me by h cross square psi. Now, in region 2, we can write the Schrodinger equation as minus h cross square by 2m d2 psi dx square plus v of psi is equals to v of psi, and we can rewrite this as d2 psi dx square is equals to 2m v naught minus e divided by h cross square psi. Okay, and we define k square as 2me by h cross square, and that means this term is defined as k square and this term is defined as q square. So q square is equals to 2m v naught minus e divided by h cross square. So far, we have defined the Schrodinger equation in different regions. Now, we have to write down the eigenfunctions. So, in region 1, we see that the particle is propagating from left to right, and then it hits the potential barrier here, and then a part of it will be reflected back. So this is the part, or this is the function which is like propagating from left to right, and this is the portion which is reflected back. In part 2, we don't have some propagating solution, and in part 3 we again have some propagating solution, but now in this case it is propagating from left to right. There is nothing that is getting reflected back, so that is why the z power minus ikx part is not present in region 3. So now we have the wave functions in 3 different regions, part 1, part 2 and part 3. Now the wave function and its first derivative must be continuous, and we just have to maintain the continuity at x equal to minus a as well as x equal to plus a. So that means at x equal to minus a, we must satisfy psi I of minus a has to be equal to psi 2 of minus a, and similarly the first derivative psi 1 dashed of minus a, this should be equal to psi 2 dashed of minus a. Correct. And similarly at this boundary, that is at x equal to plus a, we must satisfy these conditions. Note that these constant, right, in front of these functions, these are the amplitudes. For example, amplitude of the incoming wave is equal to 1. And then the amplitude of the reflected wave will be given by mod of b square, and similarly the amplitude of the outgoing wave, that is mod of f square. This is and then we expect this to be less than 1. How less, we don't know so far, and then that is why, right, you see in this diagram, since the amplitude of the transmitted wave, it reflects the transmission probability, so this has to be less than whatever was there for the incoming waves. Using the conditions for continuity of the wave functions and their first derivatives, we get 4 equations, and solving those 4 equations, we can get mod f square, which is equal to the transmission coefficient. And inverse of transmission coefficient can be represented in this form. Now we are going to plot T using different values of this parameter. Note that A is the, or 2A is the width of the potential barrier. So that means this also has to be, the term in the denominator also must be having some dimension of length. So now in this plot, we have plotted the transmission coefficient for various different values of this parameter. So for example, 0 0.1, 0 0.5 and 2.0. And what do we see? For small value of this parameter, say for example 0.1, the transmission coefficient is almost 100%. So that means the barrier is almost ignored. Whereas if you take this parameter to be very large, then the transmission coefficient is very small. That means there is almost no transmission. And for some value in between, for example 0 0.5, the transmission coefficient looks like this. Let us summarize what we have learned in this lecture. We have solved 3 classic problems in quantum mechanics. So we started with quantum harmonic oscillator, and we found that the energy eigenvalues are quantized. And we also have noticed the qualitative similarity between wave functions of quantum harmonic oscillator and particle in a box. For example, the ground state has 0 node. The first excited state has 1 node. The second excited state has 2 nodes, and so far. Then we learned about quantum free particle, and then we found that the energy eigenvalues, all of them are allowed because there is no boundary condition. And the third problem that we have learned is tunneling. We found that quantum particles can penetrate in places forbidden for classical particles. Thank you.